All right, guys, I'm recording now. All right, everyone. Can everyone see my screen well? I hope so. Okay. Okay. Right. All right, guys. So yeah, welcome to the Intro to Reinforcement Learning mini course that I put together. It's going to be 4 lectures for you. And it has a Python component. And I'll talk a little bit about how we can access it on GitHub. Yeah. So what I'm going to do today is I'm going to cover the topics that I want to get through and hopefully get through them as quickly as possible so that we can have time at the end to address any like technical issues, like how to get a GitHub account, how to download the repository, how to run programs and whatnot. If we don't get to that, we can start, we can maybe address those offline. Okay. It's very difficult when no one's responding. I feel like I'm talking to myself. Like I said, feel free to chime in. Okay, guys, well, let's get started. So today we're going to start, I'm going to introduce you guys to what eventually we will get to, like a formal setting for reinforcement learning. Before we get to that, we have to talk about a few issues, namely, how do we place a value on actions? Okay, and I'll explain what that means later, but today we're going to cover that through a model called the multi-arm bandit. Okay, I'm going to talk about, like I said, assigning values to those actions, and then how to hit either a stationary or non-stationary target. That's assigning, like, does this value shift in time? And then finally, we'll end up with what is called a contextual bandit, which brings us sort of full circle and places a square in the realm of reinforcement learning. So it's a nice little story, and I hope we can get to the reinforcement learning framework with this one lecture. Next time, we'll jump right in. It's going to have to go kind of fast. Next time, we're going to talk about dynamic programming, Monte Carlo, and temporal difference learning. These are like the cornerstones in reinforcement learning. In the third lecture, I'm gonna take a break and then talk about deep learning because it will be necessary to go further. And finally, we'll actually write some reinforcement learning program in the fourth one, and I hope I can show you guys how to apply this to your own works. So all the while during these set of 4 lectures, I want you guys to start thinking about your own projects, your own problems. And I'm hoping to have a free discussion with you guys so that we can like sort of hash out. Hello? Oh, is there someone trying to call in? Okay, so yeah, we're looking for a way to hash out how to maybe cast some of your problems in a reinforcement learning framework. Okay, so with that, let's jump right in. Okay, so like I said, the materials for the course are on my GitHub account here. So it's D Montemayor, capital RL mini course. You can see the contents in there. The way it's divided is the code is in this folder called RL mini. There's a nice README, and it should be right at the top of the page. And in it, I give you a way to, install the software in it. I use a makefile myself, but I go through like other virtual environments like VNV or Conda. Anyway, so you'll use this green button over here to clone and download and get it onto your computer. I use Atom for all of my coding. You're free to do whatever you want, whatever environment works best for you, your coding environment. I just love this, and it I can commit changes to the GitHub account through it and everything. This is all up to you. I actually can't, I don't have the time to actually go through the coding works that you guys do. So it's just considered sort of a resource. I'll introduce them as the lectures go along, and you could do some of the projects, but it's kind of like up to you. The textbook we're using in this course is going to be in this docs folder, right in there. It's a Sutton and Barto from 2018. It's a great book, and we're not going to do it justice in 4 lectures, so I highly recommend the read. Pretty much right now we're covering up to maybe chapter 2, maybe going into chapter 3 for this lecture alone. But yeah, any questions so far? None? Okay then. Let's jump in then. Okay, so the model we're going to use right now to introduce a lot of the concepts early is what we call the K-arm bandit, right? And you guys have ever heard of the one-arm bandit? You know, it's like a gambling term, right? It refers to a slot machine, right? The one-arm bandit is he steals your money, right? It's a slot machine. It has one arm. You pull the lever, and something happens, right? Some kind of you either either eats your money or you hit a jackpot, right? You could think of the reward for this one-arm bandit to be like the average value, the average return that this machine's going to give you, right? So the K-arm bandit is an extension to that, right? Now you have a slot machine with K arms. Each one of those arms then has a unique return. So that's what is shown here in this picture. In this picture, this is we have a 10-armed bandit, and what it's going to do is, you see where my cursor is, I hope. Maybe I should use the stylus. All right, so can I draw right here? Yes. What this is the average return for this first arm, and the return is actually a random number. Here it's just a Gaussian distribution, right? A normal distribution with some mean and variance. So the first arm has a return of like, I don't know what, like a half, a quarter maybe. The second arm you lose. It has a return of negative, I don't know, 0.8. So on and so forth. And so you could see here that this third arm here has the highest return, right? So it's up to you to figure out which of these arms is going to give you the best return, and then the strategy should be, we'll pull the arm that has the biggest return, right? Does that make sense to everyone so far? Yeah?
Yes.
Oh, good. All right, so we need a way to like to maybe put a number to this, right? Imagine you don't know, you can't see under the hood and you don't know what the distributions are. How would you compute this Q star of 3? Anyone? Well, what you could do is just try it a bunch of times, right? Pull that third arm a bunch of times, and then keep a running tab of the returns that you got, and then just calculate some kind of average, right? Or some distribution. So we'll say that the Q, oh man, I do not like this annotation scheme. This Q star, let's go into here. Maybe this is better. Because it's doing the same thing here. Here we go. We'll say that, this is terrible. We'll say that that Q star, my God, this is terrible. Let's use a different annotations. Maybe this works. Yeah, let's just draw. Yeah, draw lines. Okay, so we'll say that that Q for a specific action here, that's going to be just the average of the returns you get. The returns for all the points in time for, for given that you took a specific action, right? The action at time t was this eighth action, right? So this is a bracket like this, average over time. Does everyone see what I'm doing? It's a simple average, right? So here are all the returns you got at every time point, and here's the specific action you took at that time point, right? And if we assume that this is always action A, the third action, then you just take an average, the expectation averaged over all the points, and that gives you your approximate value for that action. Does that make sense to everyone so far? It's kind of like the zeroth level thing that we need to get. Yeah. All right, I'm just gonna. I need you guys to like reply, or else I just feel like I'm talking to the void here. All right. So in principle, like I said, you don't know this distribution, right? So what you're gonna have to do is guess and check, right? And so you don't know this value, so you have this estimate. Your estimate for the action value is going to be Q for that action A. Q for that action A. This is your estimate. That is going to be just the sum of all the previous actions, I, the reward you got at time I. This is a delta function. This is a delta function that means this is 0 if the action is A, and it's 1 if the action was, sorry. This is 1 if the action is A, and 0 if it wasn't the action. So we're taking all the time points, all the previous points, their returns, and if it was an action A, go ahead and count it, right? So we're just summing up over all the rewards that we got from pulling action A, and then you're just going to average over all the times that the action A was taken. So, for example, say that you came across this K-arm bandit and you interacted with it 20 times, right? And on average, you pulled one of the arms, and so 2 of those times you pulled arm 3. Okay, so this is saying let's sum up over all of them, all the 20 ones, the rewards that you got. But since this value is 0 when the action's not 3, then you're basically just going to add up all the rewards you got for action 3, and then divided by the number of actions that were when you did 3. It's just a convoluted way of writing. Just get the average value. Okay, so this is how we're going to assign a value to an action. It's just going to be a sum. It's just going to be an expectation. Okay, does that make perfect sense to everyone what we're doing?
Yes.
Yeah. Okay. So that's the first step. So that's the K-arm bandit. So what would a strategy be then? Like if you had to figure out what is the best strategy, how do you beat the K-arm bandit, or how do you get the most out of this K-arm bandit? What would you do?
Can you just pull the arm with the highest Q?
But you don't know what the Q is. Like at first, you're completely naive as to what the different arms, the returns on every arm is going to be. So what should you do? Like at step 0, you don't know anything. Anyone? Yeah, feel free to jump in, guys. Okay, so what you do is you don't know anything, right? You pick a random arm. You're going to pick a random arm and record the action, right? Next time around, you're what do you do the next on the next turn? Let's say that you picked that on that first turn, you picked arm 9 here, and you got some number along this distribution, some random number along this distribution. Maybe it was like here. Okay, what should you do on the next turn? Should you pick arm 9 again? Should you pick a new arm? What would you do?
I would choose another arm
Why would you choose another arm?
because I don't know if others are going to be higher or like are going to have higher Q or lower Q.
Exactly, exactly. You don't know. And you could kind of already have an intuition. It's probably likely, given that there's so many other arms, it's probably likely that not checking the other arms would kind of be a bad idea, right? So what you're talking about is the other basic concept in reinforcement learning, the idea of exploitation versus exploration. So what we're gonna ultimately, our strategy is going to pick the arm with the highest Q, with the highest value associated with it, right? So at the very end, after we've done this many times, presumably we've sampled these arms many times and have good averages for them. When you're in this regime, then absolutely you should always, what we say, exploit what you know and pick only the arm that has the biggest return. In the beginning, when you don't know what their averages are, then you need to explore, right? And so the idea of how to transition from a regime of exploration to a regime of exploitation is one of the fundamental blocks that we have here. Okay, so let's move on. Can I do it like this? Do I need to click on it? Probably. Do I need to click this? Am I still in annotation mode? Yep, I'm still in annotation mode. So like this. Yes. Okay, so, and how do I erase these annotations now? Clear all my drawings. Yeah. Okay, there you go. So what so you can imagine now that what we're going to have is an estimate of this average reward, and it's kind of be like a running average, right? It's you need to keep track of all the previous values that you had before in order to compute what this average is. And you can see how this can be memory intensive. If I had to keep in memory all the previous rewards, right? So the idea then is to calculate this average on the fly, right? So that I only ever keep the running total and the new value that I get at every time step. Does that make sense to what I'm saying right now to everyone? Yeah. Okay, so let's write this out. Okay, so we're saying that at that the I need to go into the draw lines. So we need to say something that the value of an action at the nth time point is the average returns. Is the average returns over all the n's, right? So average all those n returns. Okay, so we write that simply as the sum over I equals 1 to n of the returns, right? Simply like this. Returns, and then of course we divide over n. Okay, so that should be pretty clear to everyone, right? How we're going to calculate this average is just this, like we've been saying all along. Well, let's rewrite this expression and let's pull out the nth term, the last term, okay? So Q of n then is just going to be 1 over n, okay? And I'm gonna split up this sum so that over here I have the sum over I equals 1 to n minus 1 r of I. This should be an I, of course. Sorry about that, guys. This is r of I. So here I'm summing up all the, from 1 to n minus 1, and over here I've just pulled out the nth term. So you can see how this is equivalent, right? It's the sum over n, and here's the sum over 1 to n minus 1, and the nth term. Is it clear to everyone? Okay.
Yes.
Okay, so let's rewrite this. Let's keep rewriting this. Okay, so for some of you, this might be a review, like you already know how to calculate a running average, but this is how we're gonna do it here. Okay, so I'm just gonna keep on going with this then. So I have 1 over n here. That nth term is here. Now this, I'm going to insert a resolution of the identity in here. This is going to be n minus 1 over n minus 1, right? So it's just a resolution of the identity. And I take a sum over n minus 1 ri. Okay? So this is I. Okay, so you can see how this term here, the sum divided by n minus 1, that is simply going to be q to the n minus 1, right? So what we end up is a value that says 1 over n r of n plus, why does it look so weird? Wow. N minus 1 parenthesis times q of n minus 1. So that should be clear to everyone. Right? So now if I distribute this like oh, sorry, this is r of I, and so yeah, that's okay. So let's now, I need more space, so I'm going to clear. Okay, so I can rewrite that now, and I'm going to distribute that r of n over to get so 1 over n of r of n, yeah, 1 over n over r of n plus plus n of q of n minus 1 minus 1. I'm moving that n minus 1 over minus q over q of n minus 1. So I just took that n minus 1 term and I distributed. So it's n times q of n minus 1 minus 1 times q of n minus 1. That makes sense to everyone? So, so what I can do then is now just distribute this 1 over n term. So you can see that the n term is going to cancel out here. And we're going to have 1 over n r of n minus 1 over n q of n minus 1 times the plus the q of n. So we're going to, so this moves to the front and we're going to have q of n minus 1 plus, I'm distributing that 1 over n over, right? So 1 over n r of n minus q of n minus 1. Okay, so this is all like when we started. This is q of n. Okay, is this clear what the algebra I just went through to everyone? We're saying that the current estimate is going to be your previous estimate plus the current return, some fractional bit of the current return minus your previous estimate. So this is the difference between your previous estimate and what you got now times some constant. Well, it's not a constant, times some value. Is that clear to everyone?
Yes.
Yeah. So this is your old estimate. This is the error in the estimate. Error in the estimate, right? So this is your target, what we call your target. And this is the old estimate, like we just said. And so the difference between the target and the old estimate is the error. And this is some step size. Step. Oh, I can't draw. Step size. Ugh, forgive me. This is terrible penmanship with this thing. Step size. That's supposed to say step size. So this idea that your new estimate is going to be your old estimate times some error by some step size is going to be the third like fundamental block here that we're going to be using throughout reinforcement learning. Okay, so can anyone tell me then, like, how is q of n changing with respect to the error? In other words, how much do errors contribute to q of n early on versus later on, right? When I add the first term, how much does that new estimate contribute to the update versus the 100th term?
Well, the first error is going to have bigger impact than the 100th.
I'm sorry, say it again.
Like the first errors are going to have bigger impact on the average compared to the from like n greater than big N.
Yeah, and so like where does that show up in this equation?
As 1 over n.
Yeah, exactly, right? It's that nth term, right? So these contributions are going by 1 over n, right? So this, if this is a step size, this is the step size is not fixed, it's decreasing. Right? So the longer this average is going on, the more times you sample, you pull those arms on the bandit. This term is what's dictating that the new values are how much they're going to contribute to this value. So it's a decreasing step size. Okay. So this is fine and good, and we can show that it converges quite well to the true answer when the returns from these arms are fixed, right? Remember how I said that the returns on them follow some normal distribution with a mean, with this very specific mean? What if those arms changed, right? What if the casino owner said, "Hey, too many people are winning. Let's turn let's keep the the patrons on their toes and change the returns on the arms now, you know? So let's start scaling that arm that had a big return down, and maybe scaling one of the arms that had a very low return up, so that the target is now moving. Does that make sense? No, I'm still annotating. Okay. Drawings. Mouse. Is this clear to everyone?
Yes.
Okay. All right. So we now have a way to do running average. Okay. So I just talked about a moving average, but before then, I'm gonna now just introduce the simple bandit algorithm, right? So what you do is you say in the beginning, this is the value we assign to every one of those actions, every one of those arms. Initially, we're gonna set them all to 0. We don't know anything. So all the arms have a value of 0. And we're gonna keep track how many times we pulled that arm. So this is n, right? We set that all to 0, okay? And what we're gonna do then is just loop forever, okay? And we are going to choose an arm, right? How we choose it has to do with whether we're gonna do some kind of exploitative move or some random move, but let's save that for now. Point is, you picked an arm, right? And then you ask the bandit, give me the return for pulling that arm, right? And you get this value R. We're gonna say, okay, increment the counter. I pulled arm A, so increment the counter by 1, and now let's update the value for that action, for that arm, update it using the equation before, right? So it's my old value plus the error, the return I got, you know, the current return for pulling that arm, plus my minus my previous estimate, and divide that by 1 over n. This is the nth time that I've pulled that arm. So it's a really simple algorithm to do that. So here I wanted to introduce now the idea of greedy moves or random moves, right? When it comes time to choosing the arm to pick, we can pick the arm that gives us for which we have the highest estimate for. Does that make sense? So one strategy is pick the arm that we believe has the biggest return, and we're going to pick it with some probability, 1 minus e epsilon. Epsilon here is maybe it's a half, maybe it's a whatever, but this is going to determine the probability that you'll take a random choice. So I'm going to pick the best one only when I feel dictated by this epsilon value. Okay, so if epsilon was a half, then half of the time I pick the best one, and the other half I pick a random action. Does that make sense to everyone?
Quick question.
Yes.
Can the epsilon change over time? Because in the early on, you are not confident in the arc max, so you can choose high epsilon, but then later on, when you're confident, you can decrease the epsilon.
Absolutely, yeah. In fact, that's one of the most basic strategies. That in the beginning, epsilon is quite large, so most of your actions are random, and then as you get more and more statistics under your belt, then you start believing the estimates that you have, and you start exploiting them. You start picking Q, and so E maybe decreases with N. So that's that's one of the most basic strategies. So I'm glad you mentioned that. So let's for now just imagine that epsilon is just a fixed number, and then this is straight out of the book. These are results of that 10-arm bandit I showed earlier. So if epsilon is 0, it's just a greedy move. We're always going to pick the arm with the highest estimate. Okay, and so you can see how, well, if everyone started at 0, then the first one I pick, first time around, I don't know anything. They're all 0, so I pick a random action. Well, it doesn't matter. I break ties randomly. I pick a random arm. that one's going to have some finite return. And if that return is positive, then this estimate's going to go up, right? It's not going to be zero. It's going to be bigger than zero. So next time around, when it comes time to pick, if epsilon is zero, it's always the greedy one. Well, guess which arm I'm going to pick. If everyone is zero and that first one has some finite positive return, I'm going to keep picking that same arm. So when in the E greedy method, or sorry, when the epsilon is zero, the pure greedy method, you kind of lock yourself into the first arm you pick, provided it was positive. If it was negative, then like if the return was negative, then maybe you pick another one. And so that you can, here's the average reward of that strategy, picking the greedy one. You can see that the reward is, you know, so much. If you introduce some randomness, right? If you say with 1% chance, pick a random arm, then your returns improve with time because you're giving the other arms a chance to build some statistic, right? Some value. And with 10% error, I mean, this is what you get. Okay, so I hope this is very clear to everyone. This is kind of like the basic strategy here. It's the idea of exploitation versus exploration. Okay, I'm gonna have to like speed up because we're already 40 minutes into it. So, moving targets. So the previous method was very good for when you have a fixed target, right? But what if that target was moving, right? In other words, what we're seeing is that the most recent observations are more important than the really far back observations. Does that make sense? Because the target's moving, it's not fixed in time, right? So this is like a common trope in a lot of dynamic studies of dynamics, and it has many names. It's either the memory of the system, damping, you know, fluctuations from thermal noise, like, you know, Boltzmann distributions and whatnot, diffusion, basically in the limit where the in the limit where like the damping is so heavy that none of the historic observations have any impact on the current observation except for the previous, then you're in the Markovian regime, right? So how do we, so what we want then is to introduce this idea of discounted sum of rewards. We want that sum of rewards that we had in oh, well, of course I erased it. The old average, right? We want to add them up. We want to add up the most recent ones more heavily than the far distant ones, right? So how do we end up doing that? Well, we do that by that step size. Instead of it decreasing as 1 over n, we fix it. Okay, and so to drive home that point, we write the equation here. Okay, so we're going to say that q to the n, is our previous estimate, our old estimate, q to the n minus 1, plus, instead of 1 over n, let's just have a fixed step size, alpha. And then here's the error term. The return for that nth action minus your previous estimate, right? So what would that mean if I did this? What if this was a constant instead of 1 over n? Well, if I, you know, let's just expand it all out, okay? So this is equal to alpha rn plus 1 minus alpha q to the n minus 1, right? Right, so I just put this term, pulled it in here, and pulled out this term out here. Okay, And I can say that this term in here, well, let's write it like this. I'm gonna need more space. So we have alpha r to the n, and what I'm gonna do here is plus 1 minus alpha. This is terrible penmanship. Alpha what is q to the n? Well, we have the previous estimate. We could put this in here, right? So q to the n minus 1 is going to be q to the n minus 2 plus alpha r to the n minus 1 minus alpha n to the minus 2, right? So let's just put that in there. Alpha of r n minus 1 plus 1 minus alpha squared. 1 minus alpha squared q to the n minus 2. Is that clear what I just did there? I basically just recursively put that in here to calculate q to the n minus 1. And you see that this 1 minus alpha term now is now squared. Okay, so if you keep on going recursively, you're going to get a term that looks like this. You're going to say alpha, the sum over I equals 1 to n, all the n previous terms, and it's going to be 1 minus alpha to the n minus I ri. Does that make sense? So q to the n is just going to be, a term that's alpha plus the previous estimate, right? That's how this got, and then you do that with this one. And so you're just going to get a bunch of rn's, right? And the most recent one, r to the n minus 1, it is going to be squared, right? And then the third term is going to be 1 minus alpha to the third. Yeah. So, and if this is a number less than 1, then these factors decrease in time, right? It's a small number, delta, and then delta squared, and then delta to the third, and delta to the fourth. They get smaller and smaller and smaller. So we're basically, it's an average. It's a weighted average of the return, where the weight decreases the further back in time you go. Does that make sense? So this is what we mean when we say a discounted sum of rewards. This is probably the other most important aspect here. So what this does, not fixing the time, fixing the step size by alpha instead of having it a 1 over n term, we can now deal with a moving target. That's kind of like the take-home message of this slide here. Okay, so if I go to mouse and I move, all the annotations stay there, so I have to erase them. Okay, so this brings us, we got 15 minutes left, so I gotta hurry up. We have now talked about the stationary and non-stationary targets. You do that by either fixing the step size or having the 1 over n, the diminishing step size. What I want to talk about here is what happens if our initial estimates weren't 0 but rather optimistic, right? This is a strategy to help the learning algorithm, or it's not a learning algorithm, it's your calculation of the estimate. Let's instead assume that the initial estimates weren't 0 but some ridiculously high number. They were very optimistic, right? All right, so what we're gonna do, what that means is that the estimates, every time you sample an arm, the return you're gonna get is gonna probably be less than your current value. Say that you set it to 100, you pull the arm and you only get 2, right? So that, when you're updating your average, that's gonna tend to reduce its value, right? So if now all the arms start at 100, you pick one, that one's got its value reduced, all the other arms that you didn't pick still have a value of 100, right? And so if your greedy algorithm picks the arm with the highest value, then it's going to pick those arms that didn't get picked, that didn't get chosen previously. Does that make sense to everyone?
Yes.
Yeah, so this is what we call an optimistic initialization. And it's just a strategy to improve the results that you get here. So here it's completely greedy. It's completely greedy. You're not taking any random steps, but you set the initial values optimistically, and you know, so it at first it's terrible. The estimates are terrible because they're optimistic, so not anywhere near what the real values are. But because this is giving a chance of all the arms that you didn't get to pick, all the arms that haven't that are still overestimated, they get chosen. You do some effective exploration, and so that's why the returns here are better. And here is the same problem, only the initialization was all to 0, and we have a 10% random chance for exploration. So even though the initial estimates are more realistic, and if you remember, E to with the 10%, the epsilon with the 10% was the one that returned the best results of all the greedy algorithms before. This optimistic greedy can give you better returns sometimes. So, so that's one strategy: optimistic initial values. Okay. Any questions so far? All right, let's move on because I have 10 minutes. Okay, another approach that you can do is to pick those arms for which you know you have poor statistics, right? So this is called the upper confidence bound selection approach, right? So the idea here is that we're going to pick actions, we're going to pull arms according to their potential for being actually optimal, like for that the value that we have, the current estimate that we have, is actually a good one, right? And that has to do basically with the number of times you've pulled that arm, right? So like I said, yeah, you're going to take into account the uncertainty in the estimate. So the action that we're going to take, the arm, is going to be the best arm with the value. This is the current estimate, and here's a term that modifies it, right? So notice that, so C is just a constant, that the number of times you've chosen that arm appears here in the denominator. So as this number gets bigger, this value tends to decrease, meaning the uncertainty is less, right? So more times you picked it, the uncertainty is less, and so you say its value is, what your current estimate is probably good. The less times you picked it, the uncertainty is bigger, and so you say take your current estimate and add on to it a value, right? An uncertainty. So in other words, pick the upper confidence, like the 95 confidence interval, like assign its value to be optimistic, right? To be at the upper end of that confidence interval. And so those arms are going to get picked, right? Because it's a current value plus its uncertainty, okay? And here's that same problem again. Here's the E greedy at 10%, and this is using that upper confidence bound with a C of 2 estimate. So you see that the returns you get are a little better. Okay, so is everyone comfortable what we just did here? Yeah. All right, so those are just two strategies to make the learning a little more efficient. Okay, so let's move on. This is the last slide now. Okay, so well, let's take a step back. So now we have a way to determine the value of the arms on this 10-armed bandit. We can use either that upper confidence bound or the um, um, or an e-greedy method or some other way to optimize the learning. But at the end of the day, you're going to get an estimate for those the returns. And if those bandits, so if the casino was changing the returns on those bandit on those arms slowly, you can even keep up with that by using a fixed step size with a discounted sum of returns. So you can even handle a non-moving target, provided that that moving target is slow, right? So now imagine the situation where instead of having one 10-armed bandit, the casino presents you with a completely different slot machine every time. Every time the slot machine is different, all the arms are completely different, right? So that's what we say here, a random bandit is presented at each step. And you know, what we said, oh, we have a non-moving target. But in this scenario, since the returns can vary wildly, there's no reason to believe that the return of the first arm in one slot machine has anything to do with the return of the first arm and another slot machine. This fixed step size, this moving target approach isn't going to help you unless they're correlated, unless like I said, they vary smoothly, right? So this isn't going to help. So what do you do, right? This is where we say, can we use the context, right? Can we maybe before we start look at the color of the slot machine, or look at the make and model of it, or if you really want to get really specific, maybe it's serial number, right? So in other words, we're saying, are there features of the machine that we can use to identify it, and that is going to influence what action we take, right? So if it's a green slot machine, I should put arm 4. If it's a red slot machine, I should pull arm 2, right? Because each slot machine is different, and I'm going to use those features to influence my decision, right? So this is what we refer to as a policy, right? A policy is that thing that's going to govern which action to take given the current state, right? Given the current features of the bandit before you, right? And so now I hopefully have taken you from a completely like statistical sort of view now into the realm of reinforcement learning, where this policy manifested in terms of an agent is going to decide what action to take, on an environment given the current state of that environment, right? So you take the current state of the environment, the red slot machine is in front of you. Make an action. The environment is going to respond to that action in terms of a reward. It either gives you a jackpot or it doesn't, right? And it's going to change its state, right? So after you pulled the arm on the red slot machine, that slot machine goes away and now it's a green slot machine, right? So the state changes. You then use the value of the reward, right? To update your values, like we said, you know, this discounted sum of rewards if you want, to update your current estimates for the action, and you use the new state, you know, green slot machine or make or whatever to influence your next choice. And then that choice, you know, then you repeat the process over and over and over. So this is what we call the agent environment interaction, right? And that is actually going to be the topic of next lecture. So we're now square into reinforcement learning. So here I open up the floor. Please ask me questions. Please ask me questions. And yeah. And if there's some time, we can talk about some of the more technical aspects. Okay. Yeah. So also going to show you hopefully so in this course we're going to You all see the terminal I have up? Yes, no?
Yes.
Yes. So in this game, we're in this course we're gonna use a program. Remember Snake? So I coded it up for us, and it's going to be the test bed that we're going to do reinforcement learning, right? So the environment is that screen that you see before you, and the agent is doing what I'm doing. It's going to pick whether the snake moves left, right, up, down, and then hope. But this is going to, we're going to just use this to motivate our discussion. See if you can build. See if I can't die. I'm just going to die. There we go. Yeah. So that's what we're going to do. In this course, and hopefully by the end of the fourth one you'll have a snake that can get really high scores. Okay, stop the share. So yeah, so today I talked about discounted sum of rewards and how to hit a non-stationary target. We talked about exploration and exploitation, and I gave you two methods to sort of optimize that searching. And at the very end, I introduced a dynamic environment that responds to you. This is this contextual bandit example. And yeah, next time we'll do the agent environment interaction. All right, guys. Questions? Last chance. Okay. Well, then, since I only have 3 minutes, I have to step off. I'll reach out to you on via email and whatnot. And if you please try to download the GitHub repository, try to run it. See if you can't get the snake game to run. All right. And if you can do that, then we're pretty much set to go. Please email me if you have any problems, any questions, and I'll try to address your questions before the next lecture. Okay. So with that, let's say goodbye. Yeah. All right, guys.
Thanks, Dan.
Yeah.
Bye.
Bye-bye, guys.
Thank you. Bye.
Yeah, thank you.
Thank you. Bye.